today is not a day you want to miss. There's definitely optional Friday for some classes. So we now move to 5.2. Okay, we just finished 5.1. What we want to do now is instead of approximating the area, we want to find the exact area. We're going to add up the area of an infinite number of rectangles today. Here's what we say. If we have a curve we're going to say that the area bounded between A and B, we're going to call big A, it's bounded underneath f of x, the x-axis. We're going to say that that area is equal to the integral. That's now what we're in. We're in integral calculus. Kind of. Bounded from B to A. B to A. B to A. Of f of x dx. We don't know how to do that. I will teach you how to do this later. So what we're going to do is we're going to add up the area of an infinite number of rectangles. And so that's equal to the limit as n goes to infinity of the sum. It's exciting, isn't it? From I equals 1 to n of f of x sub I times delta x. So this is where delta x is equal to something and x sub I is equal to something, okay? Semicolon, yes. Yep. So YouTube Nation, the class is saying it feels like we kind of reached into a bag of alphabet soup and just like vomited it on the board. So, all right, here we go. Let's understand what the heck that means, okay? Because when I see this, that this is pure beauty and art right here. But no, you don't have to write every time you do one of those puzzles, but you do need to understand what the heck it means, and that's what we're going to try to help you out with right now. So let's get our brains in this mode. Suppose you're finding the area under the curve f of x is x squared. You're bounded from 0 to 4. Suppose you're finding the area of 8 rectangles. What's the width of each rectangle? How do you get that? So you took 4 minus 0 and you divide by 8 to get a half, right? Very good. Everybody okay with that? Concrete example? We're going to take it from concrete to abstract in a second. All right. So suppose you're finding the area of those 8 rectangles. At what x values do you evaluate the heights? Let's say we're going to do right-hand sum. You start at 0 and you go to 4, right? And if our width is a half, where do you start evaluating it at? Yep, 0.5, and then 1, then 1.5, 2, 2.5, 3, 3.5, right? So what we do is we evaluate at 0.51. We don't do it at 0, right? But I want you to understand what's happening here. This is a really important part. Everybody gets the width, but not a lot of people get this. In order to find the first spot that we evaluate the height, we move over one width, right? In order to find the second spot where we evaluate the height, we move over two widths. In order to find the third spot, we move over three widths, right? Does that make sense to everybody? Okay. So another example, okay? Suppose you're finding the area under a curve of f of x is x squared, and we're going to bound it from 3 to 4, okay? If you're finding the area of 8 rectangles, what's the width of each rectangle? How do you get that? 4 minus 3 divided by 8 is 1/8. Very good. So I'm going from 3 all the way over to 4. Where do you evaluate the first height? 3 1/8, and then, yep, or 2/8, and then 3/8, so on and so forth, right? So you don't evaluate the first height at 3, but rather 3 1/8, 3 2/8, 3 3/8. So you started at 3 and you went over 1/8, or one width, correct? And for the next one, you started 3 and you went over how many widths? 2 widths. And for the third one, you started 3 and you went over 3 widths. Okay, let's take it to the abstract. Suppose you're finding the area underneath x squared, and you're going to bound it from 3 to 5. If you're finding the area of n rectangles, what's the width of each rectangle? 2 over n. How'd you get that? Therefore, we know this, that if you're finding delta x is the width that you find by doing b minus a divided by n. Everybody good with that? We're just going to try to get this one written down, then we can go. You're finding the area of n rectangles and what x values to evaluate the height. What are you going to start at? You're going to start at 3, and you're going to go over to 5. And in order to get your first spot, you're going to take 3, and you're going to go over what? Over 2 over n. You're going to do one of those. And to get your next spot, you go from 3 and you go over 2 of the widths, right? So we start at 3 and we go over a certain number of widths. So to write that in the abstract, x sub I is, we start at A and we go over I widths. I widths. We'll show you what it means when we get back. Go get some brain food. We're going to need to be super smart for the second part, folks. So I represents the number of widths. So we're going to start at A over 1 width, 2 widths, 3 widths, 4 widths. Let's get to Callan's question. Flip it over. Here we go. We now want to find the area, the exact area, not an approximation, the exact area bounded underneath x squared from 0 to 2. We are not going to practice by using the right-hand sum. What we are going to practice doing is we're going to actually find the entire area. So we start with this, okay? What is the width? What is the width of n rectangles? We said you take b minus a divided by n. That's the width. That's what we always start with. Who can tell me what's going to be the width for these rectangles? How'd you get that, Andrew? Good. 2 over n. Yeah, stop me as soon as you have a question. Are we good there? Then we need to identify what x values do we evaluate the heights. Well, we said x sub I, or the spots where we evaluate the heights, we take a and we add it to b minus a over n times I. So what is a? 0. B minus a over n is 2 over n times I. So 2I over n. Everybody good? Okay. So the area is the integral from a to b, 0 to 2, of f of x. What's f of x? X squared dx. We don't know how to do that. We're simply saying that's what the area is, which equals the limit as n goes to infinity of the sum. We're going to sum the heights. How do we get the heights? Like, what do? We take the x values, and what do we do with those x values? We plug them into the function. So our x values are 2I over n. And if we plug them into the function, what do we do to the 2I over n? We square it. These are the x values. We plug them into the function. The function is x squared. So we get the 2I over n quantity squared. Times, okay, our delta x. What's delta x? 2 over n. Nope, that's just a comma. So when we wrote that down on the other side, just want to be clear here. This is our rule. Limit as n goes infinity of the sum from I equals 1. That means 1 width, 2 widths, 3 widths, all the way up to n widths as n goes infinity. We plug the x values into the function to get the heights, and we multiply it by the width. This is just a semicolon so that you can see that these are two pieces that we need to use. So we always take this guy and plug it in here, and this guy we always put there. Remember, it's the width times the sum of the heights, right? This is the width. This is the sum of the heights. So that's what we're going to do. We're going to take care of it. So equals, we can simplify this, the limit as n goes to infinity of the sum from I equals 1 to n of, I'm going to square this. What do you get? 4I squared over n squared times 2 over n. All we need to do is find that limit. Now, n's going to infinity. This I thing is kind of confusing me. So I'm going to use the commutative property of multiplication. I'm just going to separate it. I've got the limit as n goes to infinity, and I'm going to pull out 8 over n cubed times the sum from I equals 1 to n of what's left if I take out that 8 over n cubed. I squared. It's okay. It's okay to have levels of confusion right now, okay? We're going to work through it. Trust me. Here's what I need to do. Here's what this is saying. What do these squares add up to? So if I plug in 1, I get 1. If I plug in 2, I get 4, 9, 16, 25. Dot, 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 n squared, where n goes to infinity. The question is, what do those add up to? You might say, well, they're going to add up into infinity. I understand what you're saying, but we need a certain ratio at which they add up. Well, see if you guys remember this. This is really key. It's from last year. We did this last year. Yeah. remember? What? Very good. So this sums up to 5,050. You got it. How'd you do that, Carter? That's 101. And then 2 plus 99 is 101. 3 plus 98 is 101. And that happens how many times? 50 times, right? Do you remember when we did this? We said 1 plus 2 plus 3 plus dot, 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 dot plus n is equal to n times n plus 1 over 2. And we said, well, we're going to show that it's true for case 1. We'll show it's true for case 2. We'll assume it's true for case k, and then we'll show it's true for case k plus 1. And we use something called mathematical induction. Okay, now I'm not going to review it all, and we're not going to go it all over again. And Spencer's having a meltdown back there. Okay, don't worry about it, bud. But do you remember this? So for the people in YouTube Nation, here's what we did. We actually proved this. You're going to want to write these down somewhere where you can reference them. If you sum the first n terms, so this would be like 1 plus 2 plus 3 plus dot, 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 all the way to n. That turns out to be n times n plus 1 divided by 2. And we proved it last year. You had a test on the last day. We also proved this from I equals 1 to n of I squared. So that'll be like 1 plus 4 plus 9 plus 16 plus dot, 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 all the way to n squared. Turns out that that is n times n plus 1 times 2n plus 1 all over 6. If you ask where do we get it from, we got to prove it through mathematical induction. And we could show you. And then we have the sum from I equals 1 to n of I cubed. And we learned that that was n squared times n plus 1 quantity squared over 4. Got that? Whoops, sorry, I equals 1, sorry. And then we got just one more. It's a real simple one. What if it's not a variable? What if it's a constant? And that just ends up being the constant times however many terms you're adding up. C times n, that's it. Yep. I have them on the board right over there as well. Instead of using I use k. I and k are generally used as integers, so sorry about that. Are we good? Can I go back? Here I am. We are almost done. I want to get rid of this so that I have n's. Is there something I could put in that place? Exactly. I take this and I write it as the limit as n goes infinity of that 8 over n cubed times, you guys said I could take this and I could substitute n times n plus 1 times 2n plus 1 all over 6. Do we know how to find limits as n goes infinity? Have we done that in class before? We have. It's super easy. No big deal for us. Let's find the limit. We have the limit as n goes to infinity of, let's multiply this out. If you FOIL this, 2n and then cubed. Very good. So I have 8 over n cubed times 2n cubed plus, I have 2n times 1 and 1 times n. 3n times n. Then you do the last ones, 1 times 1, times n. That's all over 6. Okay, let's multiply those together. Got the limit as n goes to infinity. What do I have on top? So how do I do these limits and what do I factor out? Factor out an n cubed. I get 16 plus what? Plus, and that's all over 6n cubed. What happens? The n cubes cancel. What else happens? Why do they go to 0? Very good. So as n gets ridiculously large, this is going to get ridiculously small and go to 0. And so I'm left with, which is 2.6 repeating, right? Not only is it the area, it is the exact area, okay? I go here and I type in x squared and I go second calculate number 7 and I get that curve and I have a lower limit of 0 and I have an upper limit of 2 and I get to drop you.